Welcome to this simulation. In this simulation, we will explore the thermal analysis of the shell and tube heat exchanger by using dense fluid. Heat exchanger are essential component for many engineering systems, for power plants to chemical processing. Our goal in the simulation is to analyze the heat transfer between the hot fluid and the cold fluid. Hot fluid in the simulation is ethylene glycol, and the cold fluid is water. During the simulation, we are gonna looking at how the geometry is built, how boundary conditions are applied, how the results reflect the temperature distribution and turbulence inside the system. Let's begin with the simulation.
Hello everyone, in this video I will be walking you through the process of designing a heat exchanger using the ANSYS design modeler. The aim is to create a 3D model that can later be used for simulation, thermal analysis and performance evaluation. As you see, here is the workbench, and I'm gonna use fluid flow, and also you can use fluid flow with the fluid mesh. The main difference is just in the meshing process, as it doesn't quite important. You can use both. I use the fluid flow fluent, and when you click on it, you will see this geometric mesh setup solution and the results. I will proceed with the new design modeler. Let me tell the objective of the design. In this project, I'm designing a shell and tube heat exchanger. The key goal is to model the geometry accurately so that we can later run a safety simulation and successfully. Let's start with the geometry part. First, here, as you see, is an environment of new design modeler. The more important thing is to select your units. I selected the meter. So first I open the design modeler and set the unit systems to meter. Then I will create the main body for the shell and added the internal tubes. So let's start with the XY plane and choosing and click on sketch to sketch the main body. I mean the shell part. Yes. And the shell part diameter is 0.5 meter, and with the height of the 2.5. Dimension, diameter, and then choosing the diameter. And let's click on extrude and choosing your material at frozen. Then 2.5 will be our height of the main body heat exchanger. Yes, as you see here, your body has been established. Then we will proceed with the external bodies. I mean the tubes inside the shell. I will use the new sketch and sketching circles inside the tubes. This is one, and also this is two, and dimension diameter. Diameter is 0.12, as well as this 0.12. And you can easily adjust the dimension, like the vertical modes or horizontal, from here, like this. Here is yes, we can adjust on 0.12 as well, and as well as this. And 0.12, and extrude, add material, and add frozen, and the height will be the same like the main body, then generate. And we will do same for other tubes. New sketch, and the sketching, and circle, dimension, diameter. Like 0.12 and 0.12, and extrude, and you can easily adjust the vertical mode or horizontal mode and rest. I'm not gonna change this, and we will proceed with this approach, and then extrude to choose our material at frozen, 2.5 meter, then generate. Here you can easily see that our pipe has been created. Well, what's important to do now is to sketch the external body tubes. Let's we will sketch on the Z X-plane, and here we will use the new sketch and sketch other tubes for inlet and outlet of water. Circle, and we can easily sketch it here, and dimension like the diameter, and dimension will be the same like 0.12, and extrude, and it would be a bit small like 0.4, and generate, and you can easily see this is our external pipe. Okay. And also we will do same for this part. We will use the new sketch and sketching a circle here. And dimension. Would be 0.12, and extrude, yes, and the material at frozen, generate. So let me be sure that about extrusion, yes, here I made a mistake, it should be at frozen. Yes, it's now true, and for this extrusion, yes, at frozen, but the direction will be reversed. As you see here, if I click on the generate, the pipe will be reversed. As you see here, yes. Here is a good representation of our geometry. So, yes, our geometry is ready to do another things. Well, now we need to do Boolean operation. So, after modeling the internal parts, I will use Boolean operation to subtract the solid volumes and create the fluid domains. This is necessary for CFD simulation. And I'm gonna show the Boolean operation. Yes, I will click on the create and the Boolean, Then I will use subtract. Yes. So let me discuss more about the options, especially subtract, unit, intersect, and imprint faces. So let's start with the unit. What's the purpose of the unit is to combine two or more solid bodies into one single body. And subtract, what's the purpose of that is to remove the material from the one body using another body as a cutting tool. So an intersect purposes is to keep only the volume that is common between the two or more bodies. Yes. Why Boolean operations are important? Because they help simply multi-body models into single bodies, which can reduce the meshing errors. Also, they let you model the fluid domains. Also, they make it easier to set up a boundary condition and material assignments in the simulation. So let's start with the subtract, and target body will be this, and this is our target body. Yes, then apply, and body this, and also preserve. Yes, then generate. As you see here, the pipe, this external pipe from inside of the main body has been cutted. So I will use another Boolean. Target body will be this, then apply, and tool body will be our pipe inside the main body, and this is 1 and 2. Yes, 1 2 3 4. Yes, then apply, then preserve body. Yes, then generate. Okay, then what to do is I will use the Boolean operation again to make a unit from this body, and create a Boolean operation. Then I will use the unit to make a unit. This, and this. Then apply, generate. So we will see here the 5 parts, and I will make them as form a new part. Yes, this is our final geometry, and we can proceed with the meshing, and the geometry part has been completed, and we can proceed with the meshing, with appropriate meshing. Then after the meshing, we are going to proceed with the setups to introduce our boundary condition and other criteria that's necessary for simulation. Yes, we can easily proceed with the meshing part. In the meshing part, we will use edit, and we can use a double precision, and meshing processes you can use it too, and start. Well, I couldn't proceed with the full length meshing, so I tried to use full length, and I just imported my geometry inside full length. So I will just start with this edit, and we just need to a bit wait. After waiting a bit, we will see this skin, and yes, this is our geometry. We can easily make name selection to proceed. So to make selection of the name, which is quite important for us, especially important for our boundary condition, because in a setup boundary condition is a defining coding from our name selection. Here, create a name selection, and it will be hot outlet. Okay. Other area. Here. Create name and the cold inlet. Cold inlet. Here. Create a name selection. At inlet. Here. Create a name selection and the cold outlet. Okay. It's almost okay. We just need to make a body selection. Okay. And here will be batik art. And click on OK. Then we need to select the tubes inside the shell. We will hide this body. We will select this, and this. Create a name selection, pipe wall. Pipe wall. Click on OK. And then we should click on entire tubes and create name. And they should be hot domain. Hot domain. Click on OK. Well, after this procedure, we will hide on the pipes and show body, and then we will hide this. Body, and we will select this, create a name selection and the cold domain. Click on OK. Well, the name selection is OK, and the meshing procedure could be done. Show all the bodies, yes. And we can proceed with the meshing part. I will choose the sizing and this, and also this is, and apply element size. You can see the more option here in element type. I will choose the number of the division on the 75 and then generate. Yes, it's almost okay. This is the mesh criteria. So your quality of the mesh has been evaluated by this maximum aspect ratio, minimum element quality, minimum orthogonal quality, and maximum thickness. So it's almost good. If you need any refinement for your surface, you can easily make a refinement with this option. Also, we don't need to have much more cells because it leads to increase our computational time. For decrease the simulation time, we need to optimum amount of the meshes. So also I think we can proceed with this mesh. For proceeding, we need to make an update. The mesh is okay for continue our work. Yes, and we will proceed with the setup. Edit. Double precision. Also, double precision is necessary for multi-phase flow. Then start. It's the environment of setup processes. It's a quite important part. Also, each part is quite important. We've created with the name selection. As I said, it's quite important processes. You need to make a name selection to recognize your boundary. And also, here you can see the boundary conditions, cell zones, models. Our procedure is started here. We should define specific condition for our fluid. So, what is our fluids for? Cool domain, we are gonna use the water, and for the hot domain, our material will be ethylene glycol. So we need to define our material from the fluid. Yeah, we click on it, and from here, Fluent database. Here, Fluent database, we can easily select our component. One of the component is a water liquid. We will add it here. So now we have ethylene glycol and the water liquid. What's necessary to do is to define boundary condition. As you see here, with the blue arrow it's the inlet, and with the red arrow it's the outlet. So for us it's important to define the boundary condition. For boundary condition we can use mass flow, velocity inlet, pressure outlet. There is a more option to use. The more important thing is that using the models. So I will discuss a bit about this option. It's the multi-phase. If you have a multi-phase flow, you can turn on this and use some different methods like Eulerian, Lagrangian, or VOF models. So for this case, it doesn't need to choose a specific model, and the energy should be on because we are gonna solving temperature, and we just want to know the temperature profile along the heat exchanger, and these options like a species, if you have a reaction and reaction taking place inside the heat exchanger, you can use a species transport. But for this case, it's a heat exchanger. We are not gonna use this option because there isn't any reaction taking place inside the heat exchanger. So another case is to cell zone. For the cool domain, we are gonna use water liquid, then click on apply. For the hot domain, we are gonna use ethylene glycol, then click on apply. So as you see here, for the boundary condition for the inlet, we have a cold inlet and a hot inlet. So let me discuss a bit. So here is our boundary condition as we defined in the previous section in the meshing part. So for inlet, there is a different type like mass flow, outflow, pressure outlet, like symmetry, and the velocity inlet. For cold inlet, I'm gonna use a velocity inlet with the 1 meter per second, and another is good, and the thermal condition will be 193. Apply. And for hot inlet, the velocity inlet will be 1 meter per second, and the thermal condition will be 373. Then click on apply. Everything is okay. Yes. For outlet, there is a two option: cold outlet and hot outlet. For this, I'm gonna use pressure outlet, automatically chosen by ANSYS. And for hot outlet, it's on the pressure outlet. We don't need to do anything here. If I want to use mass flow inlet, okay, mass flow inlet rate, I can use like 1 point. I can use this also. It depends on your condition, but I'm not gonna use this. I'm using just with the velocity inlet. Let me to change also. Cold inlet, velocity inlet. Velocity inlet, yes, it's good. And that was 1 meter per second. Apply. For interior cold domain, we don't need to do anything. For adiabatic part or pipe wall, or we can select the thickness also, thermal, and we can use heat flux, wall thickness, or heat generation rate. If there is external, you can use heat generation rate, or if you have a wall thickness, you can add here. Maybe we can add like something like this our wall thickness for adiabatic part. And also for pipes, it's good until here. As you see here, there is a solvers. So momentum is solving with the second order equations. You can use quick, it's more precise, or pressure. You can use presto, it's quite precise. And also this in the controls, it's related to your iteration also. Under relaxation factor is completely effect on iteration procedure. I'm not gonna change this. For the monitoring, for the residual, I just use this. Then click on OK. There is just another step, initialization. There is the two option: hybrid initialization and standard initialization. I just need to do hybrid initialization, and after that we can proceed with the run calculation. Number of the iteration will be 16. I'm not gonna change this. Start the calculation. And we need to wait until all the solution converge properly. This is our continuity, so it's something like related to mass conservation. So x velocity, y velocity, z velocity, and energy equations from here make our simulation converge properly until -4 or -5. So it tells that it's the good simulation. So we need to wait until the convergence. After the simulation, we need to analyze our results. At this tutorial, we are gonna just explain the temperature profile on the heat exchanger and turbulence. For the first, we need to create a surface from the result part, surface section. Then I will create the plane along the YZ plane, then create. So immediately you will see the plane has been built here, and then we will proceed with the contour lines, and we will select all the inlets, outlets, and the pipe wall and the plane. Then we will press display. As you see here, it's our heat exchanger. From the contours, from this section, I will change this to temperature. Well, you can see different options here. We will use the static temperature here. Well, then display. You can easily see here, this is the temperature profile along the pipes and the shell parts. So, what's happening physically here? This is a control temperature across the length of the tubes. The red at the inlets shows the hot fluid entering at around 373 Kelvin. And as the fluid flows down the length of the exchanger, it gradually cools. By the time it exists, it's around 310 and 330 kelvins, depending on the location. I would say that the color transition from the red to green and blue confirms that thermal energy is being dissipated effectively, matching expected behavior in the counterflow or parallel flow exchanger. So I will change the contour from another like a turbulence, and then display. Let me just discuss with the plane. You can easily see the turbulence area. The localized turbulence peaks are present near the hot fluid inlet, top left, and possibly near the pipes. The rest of the domain is relatively stable and suggesting laminar to low turbulence areas in the core flow, which is normal in shell and tube exchanger only. And efficient turbulence near the inlet ensures better penetration and mixing. Also, it's improved the heat transfer coefficient. So overall, in the both pictures, in the first, as you see, the static temperature contours clearly illustrate a smooth temperature gradient from hot inlet to outlet, so which is a confirmed successful heat transfer across the heat exchanger. And also for the second here, the turbulence kinetic energy distribution highlights the areas of the intensified turbulence at the fluid entry zones and promoting mixing and enhancing the thermal performance while maintaining a mostly stable flow throughout the exchanger body. In conclusion, the simulation results clearly demonstrate efficient heat transfer and controlled flow behavior, and confirming that the heat exchanger design performs effectively under the given conditions. This is the end of the video, and thank you for watching this video.